First, I want to say a little about myself. I've been accused of being, quote, a shill for the nuclear industry. Actually, I didn't know anybody in the nuclear industry until a couple of weeks ago. Via Zoom, I met one of the organizers of a group that started in California and now has a branch here called Mothers for Nuclear. She worked in wind energy and now works up in on the Lake Ontario at one of the nuclear plants. Anyway, nuclear things and energy have had a major part of in my life. I was 12 years old when the bomb was dropped on Hiroshima, and I think it led directly to my becoming a physicist, getting a degree in nuclear physics at MIT. I taught physics for about a year, and I immediately in '61 joined the U.S. Arms Control and Disarmament Agency to try to control this incredibly terrible weapon. And I directed what was called the Science Policy Office in that agency, and I worked on a nuclear test ban, and I developed with my colleagues the first proposal that became the START Treaty, and I worked on non-proliferation. In the 70s, we experienced an energy crisis when the oil embargo of '73 took place, and I shifted to working on solar energy, and I produced a guide to solar energy with Arthur Waskow, who I have a feeling some of you may know. He was a colleague of mine at the Institute for Policy Studies and an old friend. I wrote a report for the Joint Economic Committee of the Congress on the employment benefits of solar energy. And then I moved to New York, and for 35 years was taught urban studies at Queens College. In 2007, I created a course, the first course there on climate change. And I taught my students what it was and that it was real. And what I told them that what has to be done about it was to expand solar and wind. We needed to eliminate the use of fossil fuels, and that nuclear energy was too risky and too expensive to be considered. But I actually hadn't looked into the numbers very carefully. And so when I retired, I decided that climate was so important that I needed to do some work on it. And I did, and I learned that I was wrong, and on both those counts. And I want to explain here why, and as concisely as I can. I hope the arguments are at least reasonably persuasive. They're, as far as I can make them, accurate. So first of all, I'm going to focus as an example on New York State, because it's close to us, it affects us. I've been working on it. It claims to be a leader in addressing climate. And so the state passed a climate law last year in the summer of 2019. It required that 10 years from now, 70% of our electricity must come from renewable energy. And 10 years later, all electricity must be carbon-free. It doesn't specify how. The legislation has some specific target for solar and wind. And it says by 2050, not only electricity, but all the rest of our energy use will have to be clean. There was and is no plan yet to achieve those goals, but the Climate Action Council, which the legislation creates, has to develop one, and it's been meeting. And I'll say a little more about it in a few minutes. So here's how New York State produces its electricity today. If I go around the circle, oil and gas is about a third. Nuclear has been about a third. Renewables are about 26%, but wind and solar are just 5% of the total. And again, that 5% by the legislation has to grow to 50% by 2030. That's the goal, a tenfold increase in wind and solar in 10 years. So I want to give you just a brief recognition of the scale of the energy sources that we have. And what I want to do is basically compare solar and wind with nuclear. I'll come back to this later, but I think it's very important to have this go. So that's a picture of the Indian Point nuclear plant up about 35 miles north of us on the Hudson River. The first of those two units, those are two reactors that you can see the containment domes above them. The first of them was shut down in May 1st, and the second one is due to shut down a year from now. And what I'm showing you in this bar is that first reactor produced more electricity over a year than all the solar and wind we've ever produced in New York State. And that goes back to the 70s, because in the 70s, the federal government instituted various subsidies for solar and wind, and New York State did too. And so in spite of the financial benefits that might bring, we still have less, that is, that one nuclear plant produced more electricity than all the solar and wind ever installed in New York State. So New York State has another peculiarity, which has a big impact, as I'll show you in a few minutes. Basically, upstate and downstate really are not well connected electrically. So upstate, most of the electricity is generated via carbon-free renewable energy and nuclear. There's the power plants on the around Niagara Falls, they're producing hydropower, and there are wind farms in Western New York and upstate New York. So the green shows that the percentage of zero emission, which is a combination of nuclear and hydro and wind, and some solar, not very much, but some. But downstate, most of the electricity that we use is generated by burning fossil fuels. The 29% that you see there is nuclear. It's basically Indian Point. That is a little more than a quarter of the electricity that we have been using in New York is generated by that plant up in Indian Point. And the interconnection between them two is very, very limited. So not much electricity can flow between the north and the south. It's like a narrow pipe that doesn't allow much to go through. The state is starting to plan how to meet those goals, and they've hired two consulting firms, one in San Francisco and one in Boston. This is the one in Boston, the Brattle Group. And I wanted to show you how they propose to meet the goal of carbon-free electricity in 2040. And the important thing I want to show you is what I've circled here, which is that offshore wind will grow from 0 right now to 25 gigawatts. Now, you don't have a scale for that, I know, but the state is planning at the moment, the state's goal at the moment is to have it grow from 0 to 9 gigawatts by 2035. So Brattle says in order to meet the 2040 goal, it should grow to 25 gigawatts. That's not the important thing, though. The important thing is that it will then supply more than a third of all the electricity that we use in New York State. Now, it's more than a third of the total, but it's basically all of the electricity downstate, because remember, it's the tale of two grids. The electricity that we use here, or that we produce in this region, that we use in this region, has to come from this region, because very little can come from upstate. So that offshore wind is basically going to be providing somewhere between 80 and 100% of the electricity in the New York City, Long Island area. And here's another model. There are three models we have now for New York. We have the group from San Francisco, the Brattle Group, and this is Mark Jacobson's model. I suspect a number of you have heard of him. He's a he's the major, most public advocate for the total 100% renewable solution to our energy problem. And he too includes a large share of the electricity, 40% of the total state electricity coming from offshore wind. And again, that's all downstate, and downstate depends on it. So again, we're talking 80 to 100% of New York City's electricity coming from offshore wind. Now, that looks all sort of nice as percentages, but you need some details. And it turns out you go to Jacobson's website, and there's a spreadsheet that gives the data for that on which that's based. It gives this data for every state and every country. They've looked around the world as well. So this is the New York part of the spreadsheet. And so I've added the data from that spreadsheet to that chart. And if you look on the lower left of that chart, you can see that we're talking about 11,500 wind turbines being built in the next 20 years. I want to call your attention mainly, though, to that dollar figure in the middle. The total cost of this, estimated by Jacobson, and it's been argued that it's low, but I won't have to argue that whether it's low or not. That's $30,000 per person, per man, woman, and child in New York State to be spent on this. Conversion from an electric system, which remember is working now. It's not working as far as the climate's concerned, but it's working as far as people's energy use is concerned. And so we're talking about $30,000 per person over the next 30 years. A reasonable estimate of what it would cost to do this with nuclear is about a third of this, but we can get into that later. I do want to point out, though, that the governor was proposing an environmental bond issue this year. He canceled it because he felt the state couldn't afford it, and it's $3 billion. So spending $600 billion is going to be a big lift for this state. That's only the state, that's not national. So it's very expensive. And here's the problem with using offshore wind. This is what the wind farm in Puerto Rico looked like after Hurricane Maria came through. Hurricane Maria was a Category 5 hurricane. We haven't had any of those yet, but we had Superstorm Sandy, as we call it. It was a Category 3 hurricane. And we know they're getting more intense. So what this model this plan is proposing is that the electricity and energy future of the downstate region will depend on a wind source that could be wiped out by a single large storm, and it would take years to come back. In other words, New York would be black out. No electricity, no lights, no elevator, no internet. No transportation, because transportation would be all electric as well under an all renewable, all electric model. So there's a problem, serious problem, but I'm going to show you more problems. One is the environmental impact of solar. We don't recognize it because it's still so small. It's still 5% of our state's electricity. But if you're going to grow it tenfold, and that's just to reach 70% of electricity. Remember, electricity is only about 20% of all the energy we use. So if you're going to expand it the way that, say, the Jacobson model has, you're going to be covering the landscape with this kind of facility. And as I say there, nothing grows on a solar farm because there's no sunlight that reaches the ground under those panels. And it requires huge amounts of land. This is a well-known solar facility out in the desert in California, Ivanpah. And it's, you can see it's huge because the solar resource is so widespread and thin that's what's it called? Diablo Canyon. That's the reactor. It's a kind of a sister reactor to Indian Point. It's on the coast, the California coast. It's also two reactors, and California is also planning to shut it down in 3 years. But whether they will or not, when they're already facing blackouts from the limitations of the reliance on solar and wind. So we often, and I've participated in these discussions, we often talk about solar and wind as being democratic because it's locally controlled, but that's going to end if we're going to place the kind of reliance on it that we're talking about. In this year, Cuomo pushed through the legislation that allows him to override any any local opposition to installing a solar or wind project above a certain size. The size is quite small. It's like 10 megawatts, which is, remember, gigawatts is 1,000 times more than a megawatt. And I mean, there are already several 10 megawatt facilities out on Long Island. So we're talking about a modest sized solar plant that the state, and there's a limit in this legislation of 1 year of review, of environmental review before the project goes ahead. So basically, my own view is you can't have both democracy and renewable energy because they require so much imposition on the land and on the space that's occupied by small towns and large ones, and require so much local. As the environmental impact is so great that it's got to be some centralized decision making. Solar and wind also are, when you think about them providing everything we need, they also are hugely demanding of resources. This is from the federal government's review of what kind of materials. This is material basically per kilowatt hour. And you can see that solar and wind are very much, substantial number of times greater demanding in their resources than nuclear plants, because nuclear is such a highly concentrated energy. That was the point of my scale comparison earlier, that one small plant produces more electricity than all the solar and wind in the state right now. And those materials are not benign. They require mining, particularly in developing areas in China and Mongolia, African countries. It's going to have a huge impact. The UN and the World Bank are already looking at that and trying to talk about sort of environmentally sensitive mining. And then after the solar facilities and wind facilities will last, maybe they each have lifetimes of about 20 years. What you see on the left is solar panels in Puerto Rico after Hurricane Maria, but after 20 years, they'll have to be scrapped and replaced with new ones. They deteriorate over time just from weather and aging. And you're going to get huge waste piles piling up everywhere, or wherever you can find some place to take them and dump it. And there's wind turbine fans, which are also they're a very special ceramic and they're not easily recycled or decomposed. It's often argued that the reason that renewables have developed so slowly is because of opposition from the fossil fuel industry. But in fact, if you see the bottom line there, BP recognizes, and others in the industry do, that they're the perfect partner for renewables, because renewables, solar and wind, are intermittent sources. The sun isn't shining at night, the wind isn't always blowing, and what do you do when that happens? And today, what we do is we turn to fossil fuels. We burn natural gas or oil to generate electricity because we want to keep the lights on. And they don't like nuclear because they know that nuclear can replace them. This is a flyer when a few years ago, the Cuomo was supporting subsidies for the nuclear facilities on Lake Ontario, which the locals up there like because they produce jobs, good paying jobs, and tax revenue. And that's the American Petroleum Institute sponsoring the ad against nuclear. Now, there's what I consider a bit of a breakthrough. This is from 2 days ago. The New York ISO, Independent System Operator, they're the people who run the electric grid of New York State. It's a nonprofit. You would think it was part of the government, but it's a nonprofit that runs, because the electric system is mostly private, and so they coordinate and operate the grid. Their computers signal what facilities will go on and go off as depending on the demand for electricity. And they gave a presentation, excuse me, just 2 days ago to the Climate Action Council, which remember is supposed to be coming up with a plan for our energy future. And they said their studies say that the renewables they can identify won't do the job. That's what that diagram is showing. What I've circled there is a 7-day period during the summer in which the gray area is the gap. The top of the graph, the little black line, that's the demand. That's our use of electricity during that week. Goes up in the daytime and down somewhat at night. But what you can see if you look at the colors is that the offshore wind that it's depending on dies down during the summer. And wind, the wind turbine output is very sensitive to wind speed. If you're into little mathematics, it goes like the cube of the wind speed. So if the wind speed drops by a half, the output drops to 1/8 of what it was. And that's what's happened there. During the summer, well, I guess it's ironic. In the summer, we either get the storms that knock out the wind turbines or that force them to shut down so they don't get damaged while the storm is coming through, or we get no wind at all. And that's what that's showing. And so what the ISO folks said to the Climate Action Council is the renewables we've been able to identify so far simply won't do the job of meeting our electricity demand that we forecast for 2040. Now their answers, I show there, this is their slide, are market solutions to drive investment and development of innovative new technologies. They wouldn't say the word nuclear, I think because the Cuomo administration opposes it, but nuclear exists and can meet that need. And that's what I want to turn to now. But what I'm showing you is that the people who run the grid have identified an absolute need to find something that's carbon free and that can fill in when wind and solar aren't adequate to meet the demand that we have. So let me now turn from the discussion of the limitations of solar and wind to the question of nuclear, and is it safe, and is it reliable, and is it realistic? So first of all, I'm asserting that nuclear power can address the inadequacies of a dependence on renewable sources. Unfortunately, as you know, and as I knew, many of us believe, and I used to believe, that nuclear energy was too dangerous for us to use. And the result is we don't have a good answer. That is, you could see that the ISO people have no answer to what do we do about getting rid of fossil fuels if the renewables aren't adequate to do the job. And we've got to act. And my assertion, what I want to show you is that nuclear plants can provide reliable, continuous power with very low environmental impact. And the waste is tiny compared to the waste I just showed you from renewables, from what happens when they need to be scrapped. And of course, from fossil fuels, where you get mountains of, you get pollution of all kinds. I don't need to tell this group about that. So let me talk about nuclear waste. So here's a slide showing some nuclear waste. This is what it looks like, how it's stored in these casks. They're basically fuel rods that are stored away after they've been used. all the waste in the United States could fit in that ball field. And they emit very little radiation and don't, in fact, pose any danger to anyone. The reason, I know what worries people is the radioactivity lasts so long, but if you think about it, it lasts so long because the radiation is so weak. That is, the materials are decaying. They're emitting alpha rays, beta rays, gamma rays, actually alpha and beta particles to be more specific. But they're emitting them so slowly that it lasts, the radioactivity lasts a long time, but it's very, very weak radiation. Here I have found this picture. This is Indian Point. That's the Indian Point plant. And there's the waste from the Indian Point plant. That's 50 years of waste. The plant's been operating since '74. And that's its waste. It's not a big environmental issue. Now, people will say, well, there's no solution. Well, there's now a solution. Here's an environmental group in California. It's a company now has a product that basically wants to sell of what to do with the waste. And basically you want to use, and there's a nice video you can find online that will show them doing it. They want to use basically the technology that's been developed for fracking. You drill a hole, say a mile down, you go horizontal then, and you send the fuel rods down there, and they're stored basically forever. They're never going to have any human impact. But one of the nice things about them is that you can actually get them back. You can pull them back out again if you want to use it, because, and I'll get to this in a few minutes, because much of the material in those fuel rods is still usable as nuclear fuel if you use the proper kind of reactor. And I'll get back to that in a few minutes. There's the issue of cost. I think this diagram comes from the paper that I've cited there. It shows the cost of nuclear over time. The blue is the United States. And after 3 Mile Island, which I'll come to in a minute, we started to institute many more environmental regulations, and the costs started to go up, and then we didn't build anymore. It's interesting that we didn't build anymore. The reason is that electricity use after the energy crisis of the 70s leveled off, and we've become much more efficient. So we're actually using as much energy today as we were 30 years ago, and as much electricity. So there wasn't a market for building new plants, so we didn't build them. But other countries are building them, and you can see their costs. And they're actually using the more recent ones that South Korea and the Chinese are building are actually American designs. That AP1000 that the Chinese, they built a number of them. Now they're Westinghouse designs. We can, if we go back to learning what we knew, can in fact make them much more inexpensively than we are. But there are other reasons too, because there are new kinds of nuclear facilities, which first of all can't melt down. That is just their physical properties. They either automatically shut down because they get heated, they expand, and the expansion means they're no longer critical, so the reaction stops. They can be built in factories. They're small, they built in factories rather than on site. They can consume, as I suggested a few minutes ago, they can consume the existing nuclear waste as fuel, because most of that waste is simply uranium-238. And it's not radioactive in any significant way. Its half-life is 4 billion years. But it can be converted to plutonium and be a fuel inside a reactor. So with what's called a breeder reactor or a fast neutron reactor, it can be used as fuel, produce essentially an endless supply of fuel from the existing fuel rods. And many countries are developing these new models. I mean, here's a picture of one. This is the GE Hitachi integral fuel reactor, IFR it's called. It's you can see it's kind of a factory built kind of thing. Here's a drawing or a picture of what it would look like taking one out to a site. And here's a vision of what it could be like. It could power a city with no carbon emissions and limited impact on the surrounding environment. Now, I want to talk about radiation because that's the real concern I think that a lot of people have. So I've actually learned a lot about it in the last couple of years. So first of all, we live in a bath of radiation. The world is radioactive. All the rocks in the earth, the food we eat, the banana I have every morning for breakfast is radioactive. Our bodies are radioactive. So that's called background radiation. And life emerged on this planet in the midst of that kind of radioactive background. And the DNA developed biological mechanisms to protect itself and allow itself to be repaired from exposure to background radiation. In fact, we're exposed to far more natural radiation than radiation from man-made sources. I'll show you that in a second. But the doses of this radiation vary. If you live in Denver, if you live in the Rocky Mountains, some of the radiation comes from outer space, cosmic rays we used to call it. And so they get a higher level of background radiation than those of us living at sea level, but there's no variation in health. There's no, they don't suffer cancers any more than we do because low-level radiation, which is what that is, small amounts of radiation, just don't create serious health problems. Here's a figure from the most recent report of the National Academy of Sciences. And what it shows in the lower part is that 82% of the radiation we're exposed to today in the US is this natural background radiation I'm talking about. Most of the rest is we want, that is, it's medical x-rays, CT scans, nuclear radiation to try to cure cancers. There's high intensity beams that kill cancer cells. About 1% comes from nuclear power from the results of the use of nuclear facilities to generate electricity. So here's a scale of it. The unit is called the millisievert. It used to be called a rem. Most of us remember rems, but millisievert is oriented towards what its biological impact is rather than how many electrons are given off. So first of all, scale. You can see I'm trying to show here the scale. The emergency workers at Chernobyl who died, there were about 28 of them. They received doses of 5,000 millisieverts. The general research has shown that about 100 millisieverts, it's the smallest dose that will produce an increased cancer risk. So it's 50 times smaller than what killed those workers. And the background radiation is about 2 or 3 millisieverts. So the general radiation we receive, but you can see that if you're an airplane pilot, you'll be exposed to about 9 over the year, flying back and forth at 30,000 feet. If you go for a CT scan, which I suspect most of us have had, you get 10 or 15. And what I've got here is a quote from the scientific committee set up by the UN to look at the effects of these various nuclear experiences we have. And they found that the additional exposure received by most Japanese as a result of the Fukushima meltdown are less than the dose they received from natural background. It's not a large dose. It's the dose that we all get just by living on this earth. So let me talk about the 3 nuclear accidents that are taken often as a demonstration that nuclear is unsafe. But you can actually, if you look at what the actual facts are, turns out they're the best evidence we have that nuclear is the safest energy source we have compared to all the rest. first of all, 3 Mile Island, in which a reactor melted down, but there were no outside effect. There were no deaths, and the actual release of radiation was so small that it has a negligible effect on the physical health of individuals. This is from the President's Commission, the Kemeny Commission that was set up at the time, back in '79. And then there's Chernobyl. The known deaths are 28, and the UN scientists say there's no persuasive evidence of any other health effect. Now, there was another health effect. There was, because we know there was thyroid, there was iodine 131 released when the reactor basically caught fire through stupidity of the people who both designed it and then tried to run a test. There certainly were additional cases of thyroid cancer, but compared to the general background, it's not possible to identify any place where there was an increase in the effects, increase in that kind of cancer or any other as a result of the radiation that was released in that accident. Of course, no country, no one anymore would ever operate a reactor like the one at Chernobyl, which had no containment vessel, no containment over the reactor, for instance. And then there's Fukushima. A lot of people, Fukushima, convinced that nuclear is safe because 3 reactors melted down. There were no deaths as a result of the accident. And the scientists find that there's no discernible difference from pre-existing levels due to radiation exposure of illness of any kind. Again, there was radiation released, but it's at this low level where you can't see it, distinguish it from the general background of radiation that we already have. You can go out with a detector and you can detect individual releases of beta rays, beta particles with a detector. But in terms of its impact on people, there is no discernible effect on people. Now, since I want to present you with one more mind-blowing thing, which at least it was to me. This is looking at those of us who have owned private homes or bought private homes in the last 20, 30 years know that you always, these days you have to have a radon check, particularly if you have a basement, to see if what the level of radon is, which is a radioactive gas. And so this is, Bernard Cohen was a very famous, well-respected physicist, University of Pittsburgh, who decided to look at see if he could identify the impact of radon on people's health. And you expect that the higher the dose, the mean radon level, the more lung cancer you would get in particular. So he got data for every county in the country. And the result, in fact, was that the lower the higher the dose, the lower at the levels that radon appears, the lower the rate of lung cancer, the number of cases of lung cancer. And this has been tested and retested. He corrected it for smoking because that's the major cause of lung cancer. And it holds up. And one of the sources in here, the second one, the title of the article is Residential Radon Appears to Prevent Lung Cancer. They actually did not this kind of, I think, what's called an ecological study, which you look at a whole county, but they went to individual patients, individual homes, measured the radon level in individual homes, and then correlated it with the rate with the cancer rates. And they found the same thing. The lower the higher the rate of radon, the lower the rate of cancer. There's what's happening, at least the interpretation of this, is there's a phenomenon called hormesis, in which exposure of DNA and cells to insults of various kinds, whether it's chemicals or radiation, activates a protective restoration mechanism, which reduces, which kills things like cancer, lung cancer cells. And people are actually using low-level radiation. This is not the kind of radiation you would use if you want to, if somebody has a cancer and you want to kill it with radiation. This is very low-level radiation, but people are using it to cure infections in people's lungs by exposing them to a low level of radiation, which then stimulates the cells to repair themselves. And that seems to be what's happening here. That if you have enough radon, it is protective against lung cancer. It's the exact opposite of what you'd expect and what, in fact, what the radiation standards are based on, because they're all based on that blue line. They're based on the assumption that the more radiation, even at very low levels, where it's very, very hard to measure effects, even at low levels, you still have that dose dependence. I think basically, if you look at things realistically, my conclusions, my set of conclusions, which is one, that solar and wind are too weak, too unreliable, and too costly to power the kind of modern society we've created. Now, you can of course go back to, there are people who say, well, we got to go back to some form of natural living, but here in New York City, it's a little hard to envision that, and solar and wind just can't power a New York City. And particularly wind, being offshore and subject to storms, and storms on the one hand and slack wind on the other, is not just, I don't want to get stuck in the elevator when the wind dies out on the shore. Nuclear power is the only carbon-free source we have today that can expand and is safe and reliable. And as I said, if you look at it, if you look at the actual impacts of those three accidents that have happened, it is a safe source compared to all the others. Now, it's, I have to say compared. I mean, if we had our druthers, we'd have something that was even safer, but this is the real world, and that's what we have. And further, there are now new types of reactors that are coming in, and it will start to be installed in this decade, that'll be even safer. That is, they can't melt down at all. They will leave minor amounts of waste because they'll eat up the waste that we now have. And they'll cost a lot less than what renewables would cost. The real reason renewables cost so much, the Jacobson plant, for instance, is you have to overbuild them so much because they're intermittent. Because you want to you need to be able to survive when you don't have enough wind or at night, so you can store it in batteries or something. But you can't store in batteries enough electricity to power New York City for a week. So, all right, that's, I think I probably have presented more than enough, and I'll be